Hey everybody. I just kind of wanted to go through some of these practice problems with you guys. So homework number 1, a rectangular schoolyard is to be fenced in using the wall of the school for one side and 150 meters of fencing for the other 3 sides. So I'm just going to kind of draw this out right here. So if this is the school wall, I'm just going to put school, and I'm using my slate, so I'm sorry if my handwriting looks really dumb. Okay, and this is going to be like an aerial view. So we're looking at the school from up above, right? And then here's the yard out here. And so the other 3 sides of this are going to be with 150 meters of fencing. So all around here, this is going to be fencing. And so all of this orange part has to add up to 150 meters. So the area, which is represented by A of x, in square meters of the schoolyard is a function of the length x in meters of each of the sides perpendicular to the school wall. So what this statement means right here is that this length right here is x, and this length right here is x. So what we need to do is we need to write an expression for A of x. So if we think about all the length of this orange here has to add up to 150. So if we started with 150 meters of fencing and we're letting these 2 sides be x, then the distance here would have to be 150 minus 2x. So that's this length right here, 150 minus 2x. Okay, now when we find the area of something, because that's what it's asking us for, this question is basically asking us to find an expression that will help us figure out what the area is. So if you think about finding the area of a rectangle, you just take the length times the width. So in this case, the expression that we would have for A of x is equal to 150 minus 2x times x. And the second part of this question is, what is the area of the schoolyard when x is equal to 20? So all we have to do is substitute 20 in wherever we see x. So where it's basically asking us, what is A of 20? A of 20 is just 150 minus 2 times 20 times 20. So 2 times 20 is 40, so 150 minus 40 would be 110, and then 110 times 20, I had a different number written down on my thing. Whoops. Maybe. Oh, here. Ugh, you guys. Okay, so we've got 150 minus 40 is 110, so then we're taking 110. And it's not going to work. 110 times 20. Sorry, okay, so that would give us the area when the side length is 20 would be equal to 2,200 square meters. Okay. And the last part of A is asking for what is a reasonable domain for A in this context. So let me undo this. Actually, I'm going to back up. Okay. What is a reasonable domain for A in this context? Well, we can't have an area of 0, right? And so if we put a 0 in here, that's going to make this whole thing equal to 0. So I know that it has to be bigger than 0. So I'm going to put my domain over here, and I'm going to use a different kind of notation. So like a parentheses bracket just means we don't include that number, and if you use a square bracket, that means that we do include that number. So in this case, I'm going to put a 0 here because we can't have an area of 0. So I know that my domain which is my side length, has to be greater than 0. But the other thing that's going to give me a 0 here is a 75, because if I take 150 minus 2 times 75, 2 times 75 is 150. That's going to give me a 0 here as well. So my interval would be between 0 and 75. And I know that this looks like an ordered pair, but in the context of asking for domain, this actually means that x has to be in between 0 and 75. And these curved brackets here just tell us that those numbers are not included in that domain. Okay, number 2, so Noah finds an expression that gives the volume of an open top box, so kind of like what we discussed in class the other day, in cubic inches in terms of the length x in inches of the cutout squares used to make it. So basically what that is saying is just like what we had yesterday. So we started off with a sheet of paper, and what we did is we cut the corners out so that we could fold those sides up to make a box. Okay, so we cut out these corners right here. Okay, so this is the graph that Noah gets if he allows x to take on any value between -1 and 5. So if you look at the graph, and now think about this because this is for the graph of volume. So if you think about what makes sense for volume, does it make sense that we could have a negative volume or a negative side length? Because x, remember, is the side length of these cutouts. So would it make sense for one of those cutouts to have a side length of -1? No, not really. So a more appropriate domain for Noah would be from 0, okay, and again, I'm going to use these curved brackets here to show that we're not really including 0, but anything bigger than that would work. And then if you look at where this goes negative again, sorry, down here, so the y values represent volume. So as long as this volume is positive, then we're fine. But once this volume becomes negative down here, now anything that's below this is not going to make sense. And likewise, anything that's farther over this way is not going to make sense. So our domain should be from 0 to 2.5. And again, curved bracket because we're not actually including 2.5, because when we have 2.5, that volume is also equal to 0. So the approximate maximum value for his box, so this x-axis represents the cutout squares, the side of those cutout squares. So one side of these little squares up here. The curve, the y value, actually represents the volume of the box. So if you find the highest point of the box and you follow it over to where it would hit the y-axis, then that would tell you what the approximate maximum value of that box is. And in this case, it's 15 cubic centimeters. Sorry, inches. This should be inches. Cubic inches. Okay, number 3, Mai wants to make an open top box by cutting out corners of a square piece of cardboard and folding up the sides. So again, similar to the problem that we worked on in class yesterday and similar to the previous problem. So we have and this time it's a square piece of paper, so it's a 10 by 10. Okay, and again, we're cutting out these corners here. And this distance here, I'll mark this in a different color. This distance here is x. Okay, and this distance all along here is 10. Okay, so again, this distance right here is also x. And the volume in cubic centimeters is a function of the side length of these square cutouts. So we want to write an expression for the volume of this box. So the volume in terms of x. So this is similar to what we did in class yesterday. We know that volume is going to be length times width times height. Okay, and the length and the width here are actually the same. And remember that the height is going to be the same as whatever side length this cutout is. So your height is actually going to be whatever x is. So in order to find your length, we know that we're starting out with 10, but we're not using the whole side of this. We're taking an x out over here and we're taking an x out over here. So this distance right here is actually 10, but we're subtracting out 2 x's. So this distance here, our length would be 10 minus 2x. And since this is the same, it's actually, we can write this as squared, and then we're multiplying that times x because that's our height. So the length and the width are the same, and when you have two of the same thing that you're multiplying together, you can actually just square it. If you don't like that squaring idea, you can just do 10 minus 2x times 10 minus 2x times x. So that would be your expression for the volume of x. This would be equal to the volume of the box. So the next question, the next part of this question is just asking what's the volume of the box if x is equal to 3. So if we cut out a 3-inch chunk over here on each one of these, right, we just have to figure out what that, interesting, I have a little asterisk on here. That's nice. Let's get rid of you, little asterisk. Okay, so if we want to find the volume of the box when x is equal to 3, we just have to plug 3 in, substitute 3 in wherever we see an x. So we have 10 minus 2 times 3, and that actually we can just square and then multiply that times 3. So 10 minus 6 is 4. 4 squared is 16, and 16 times 3 is 48. So it would be 48 centimeters cubed. All right, homework number 4. The area of a pond covered by algae is 1/4 of a square meter on day 1, and it doubles each day. So these 4, 5, and 6 are all kind of review from unit 1. So on day 1, which we can see right here, we know that the algae covers 1/4 of a square meter. So 1/4 of a square meter. The next day it doubles. So if you look, it kind of converts this into decimals for us. So 1/4 doubled would be 50 cents or 1/2. And then half doubled would be 1. And then 1 doubled would be 2. And then 2 doubled would be 4. And then 4 doubled would be 8. And that's all that question is asking you for. Question number 5 is asking us to define this sequence recursively. So if you remember, a recursive function has 3 parts. It has the initial value, it has the actual rule itself, and then it has the domain. Okay, so for the initial value, the very first thing that we want to do is we want to determine whether this is arithmetic or geometric. And then based on that, find out whatever the growth factor or the common difference is. So if we take, we can see that the distance between these is not the same if we add or subtract. And so we know that this is geometric. And to find the common ratio, we just take the last number and divide it by the one right before it. So 0.5 divided by 5, and that gives us 1/10 or 0.1. So this is our growth factor for this sequence here. So now all we have to do is just list each one of these 3 pieces. So the first one, the initial value, is just the first number of the sequence. So the first number of the sequence is 5,000. Oh, and they're using P of n, so I should have a P here, sorry. So P of 1 is equal to 5,000. The next thing we want to do is write the rule for the rest of the outputs. So all we're doing is we're saying, okay, so from here we have a 5,000. That's our starting point. Now we have to know how to get to 500. We have to know how to get this output, this output, this output, and any other output. So we're going to say for any other output, that's what P of n is the output. We're going to take the output before, which is n minus 1. So if this is P of n, the one before it is P of n minus 1. If this is P of n, this is P of n minus 1. And then since this is geometric, we're multiplying, and we're multiplying by that growth factor. So P of n minus 1 times 1/10. And then the domain is just 1 larger than this number right here. So this would be n is greater than or equal to 2. And when you define that recursively, you have to make sure that you get every single part of that function in order for it to count as your recursive definition. Okay, and on the last question, we've got some sloth information here. So the first thing it's asking us to do is describe a pattern and how each population changed from one year to the next. So if you look at population number 1 is the subsequent year is 85% of the previous year. So the population is 85% of the previous year. Okay, population 2 decreases by 2 each year. Okay, so using that information, we just want to figure out what each one of these next terms is, or what these outputs are. So after 47, you'd have 39.95. And then for the other population, it would be 29 because you're just subtracting 2. So the way that I got 39.95 is to take 47 times 0.85, because if you divide each one of these by the one before it, you get 0.85. So I'm going to multiply to get the next one. So that would be 33.96 rounded, and then over here it would be 27. The next one down would be 28.86, and then the next one over here would be 25, and then down here we'd have 24.5, and over here, 24.5, and then over here we'd have 23. And so if we plot each one of these, and I'm not going to plot this on the graph, I think you guys can probably do this, because you would just use, so one ordered pair would be 0.90, 176.5, and then the other ordered pairs would be 0.39, 137, 235, and so on. Then the last question is asking, does population 2 ever equal population 1? If so, when? And explain or show your reasoning. So this one, you would probably have to extend your graph out quite a ways in order for you to see where they do cross. They will eventually cross, and I believe that they cross in more than one spot. But you would have to extend this graph out a little ways. If you wanted to, you could go to Desmos.com and type in these two functions. You could come up with an explicit function for both of these and graph them on Desmos and find out where they intersect. If you have questions, please let me know.